Okay guys, so let us continue that we designed the controller analytically for the plant that has no integrator a topological transfer function and wants to follow simply non-zero reference input or desirable inputs, right? So in the previous class we said that this LTI system, that I'm going to extend this to the MIMO system by example, and be AX plus BU, and the Y is equal to CX. So we added a parameter that adding to the order of the system by 1 is going to be R minus Y, which is R minus CX, that's right. And we said that let me see exactly, I don't want to give you false information. We said that we said what? We said we said that the control design was minus k modified x, that if you look at the part 15, plus k first element of that in zeta modified. Please go and look at this part 15, that how we derive this modified. That's right. Because remember that the state space from the previous class ended to, remember, x dot of e and the zeta dot of e, that was equal to, your A matrix we named as A hat, A original A 0, C vector 0, and we named this as A hat, remember from the previous class. And this is xe and zeta e, and also we modified the B vector, so B0 UE. So this is how we added to the order of the systems, right? And we named this as B hat. So now let's go to example, because and implement in the Matlab, because if we cannot do that, all the things that we are developing sucks. Okay, so this is the particle mass and pendulum, and this is ML, and we want to just move it from here to here, that's right, theta, and this is point O. And you know from the dynamic course that first step, we are starting from scratch, is to apply the moment equation for the rotational motions, and this is the sum of the moments around fixed point or mass center. This is the mass moment of inertia, and this is the angular velocity. You have to know this from the dynamics of the graduate course. So that's why you have to draw the free body diagram. You have only two things. One of them is U, the control that you're going to design here today in analytically and also in Matlab. So this is going to be mg in this distance. This is L sine theta from trigonometry of the kindergarten. L sine theta. And the sign of that plus or minus, I told you several times on the graduate courses that is plus, because you want to come from here to here. So this mg helping the motion gonna be plus, and the plus u obviously is ml squared. You know, this is particle mass, so it's around its own mass center is 0, so plus md squared. This is dynamic course. You can find it in the Google even. So, and suppose that I'm gonna, because this is nonlinear equation of the motion, obviously I have to linearize around the covariant point of 0. That's right, covariant point of 0. Here is covariant point of 0. this equilibrium point after 0. Now I have a question from you. If your boss says this equilibrium point is stable or unstable, what's gonna be your answer mathematically? Obviously this equilibrium point gonna be let us see. So what we're gonna do, I'm gonna say x1 is equal to theta, because we are going to state space. X2 is equal to theta dot. Having the time derivative, it gives me x dot 1 is equal to theta dot, which is x2. We are going to state variable as we're going to do in the Matlab. X dot 2 gonna be theta double dot. Theta double dot is this. See, the double dot. Gonna be 1 ml square u controller plus mgl sine of what is theta? x1, because we are going to state spaces, right? So look at here, guys. So the state space nonlinear state space equation is this, guys. X dot 1 is equal to x2, and the x dot 2 gonna be 1 over ml square, the controller that we're going to design to implement Matlab, plus mgl sine of x1. Everything is based on state variables, right? But now we know from mathematics that this, I taught you, we have several equilibrium points for the system. 0 plus minus pi plus minus 2 pi and forever. How? If you look at the original problem, original equation of the motion, mgl sine of theta plus u. This was the original one, that's right. So equilibrium point means that if there is no external force, your system remains stationary. So it means that your system has no velocity and acceleration. The double is acceleration. So you're gonna get sine of theta is 0, which is sine of what? K pi. When the k is 0 plus minus 1 plus minus 2, and that's why you reach here. So these are lots of theorems and dilemmas in the nonlinear control course. I don't want to teach you those, but please accept from me, okay? Now we're going to judge about the stability of the equilibrium points. You have to make the Jacobian matrix, not the robotics one that I'm teaching this semester. This is the control, because you have two state variables. You're going to be 2 by 2 matrix. I taught you previously in this course. It's round f1 over round x1. If this is f1, you have to name like this. This is f2, and you have more f3, f2. That's right. So round f1 over round x2. Here, round f2 over round x1 again, and the round partial derivative of f1 versus f2 with respect to round x2. So let us do that together, huh? This is very easy. To judge about the stability or instability of the equilibrium points. Do you see here x1? No, here is gonna be 0. Do you see x2 here? Yes, it's gonna be 1. Partial derivative. Do you see any x1 here? Yes. So what you're gonna have is m with m goes, l is gonna be g over l. That's right. Cosine x1 partial derivative. Sine is cosine. That's right. G over L. So do you see x2 here? No, 0. Here we go. We got that. Now we have to evaluate this using the eigenvalue problem that I taught you several times. Eigenvalue problem. To get what? Problem. To get what? Eigenvalues of the system. Because I taught you, eigenvalues are the poles of the system. Remember? Eigenvalues is another hand the linear system, or they are the poles of the system. So I'm going to evaluate that. J, the Jacobian at first, at 0. Look at here, guys, around this point. Okay, so it's gonna be 0, 1. So cosine of 0 is 1, so it's gonna be G over L and the 0. Suppose G is 10 meter per second, L is 1 meter. That's right, you are in the SI system, meter per second square. So your J, Jacobian matrix, is gonna be 0, 1, 10, 0. So what is the eigenvalue problem? I taught you previously. Lambda I minus J here is 0. Determinant of that. So lambda I, for God's sake, is lambda 0, 0, lambda. Identity matrix. This is identity matrix. Minus J, 0, 1, 10, 0. This determinant is 0. So what you're gonna get is this: lambda minus 1 minus 10 and 0. Oh, sorry, on lambda, right? This determinant is 0. Determinant of 0 means gives you lambda square minus plus, gonna be minus 10 is 0. Bingo. Now we have two poles or two eigenvalues by linearization around the equilibrium points. Okay, so lambda 1 and lambda 2 will be plus minus from here, plus minus 10. And this is the rule in nonlinear control. This is the result I'm teaching you. There are lots of theories and lemmas, okay? But this is not nonlinear control course. If real part of, because your eigenvalues can be a complex number like this, right? Generally, if real part of eigenvalue is positive, your system, your equilibrium points here, equilibrium point is unstable. So we see that theta hat 0 is unstable, and this is because if by assumption that there is no friction here as we did here, so if we leave it here, it's gonna move. So there is no stationary point here, it's gonna move, so it's unstable. Now if you evaluate around, say, if you say pi, the second one, pi is this, guys, pi is this point. Here's pi, that's right, at the bottom, that's right. So if you say Jacobian at the pi, so your Jacobian becomes like this: 0, 1, cosine of pi is minus 1, gonna be minus 10 and 0.
I can learn to understand you much better if I can get familiar with the way you talk.
What? So if you solve the eigenvalue problem, you get this finally at the end of the day: minus 1 plus 10 and lambda and 0. So you get from here lambda square, that's right, plus 10 is 0. You get from here, you have two eigenvalues, see, plus minus I, because this goes here is gonna be minus 10 this side, I. So you have a pair of pure imaginary number. So there is no rule in the nonlinear control. If the real part is 0, we cannot judge about the stability or instability of the system. But as I taught you that the eigenvalues are the poles of the system, you see that the system going to be marginally stable, going to oscillate forever. Okay? So, but we cannot judge it. We cannot judge it. So, you see that this is unstable equilibrium point. I wanted to show you what's that. If you hear when you go to industry, this is unstable equilibrium point. Okay, this is unstable equilibrium points. Now we can linearize around that. You can say x dot 1 is equal to x2. Oh. What happened? Is equal to x2, and now x dot 2 is equal to 1 over ml square u plus, see here we go. Now sign around the equivalent point of 0 gonna be x1. You know this by using the Taylor series expansions, right? Or the Jacobian matrix here. Gonna be x1. Here we go. Now we have linearized, we have the LTI system. Okay? But we have to design a controller because I'm gonna keep the angle of that at what? At 10. This is desirable that I want to have a 10 degree. So, but based on whatever, okay, this is one, okay? This is the state space. But guys, look at here. We're gonna transfer this in the Matlab, okay? Guys, original system was this, look at here. ml square theta double dot is equal to mgl plus u, mgl sine theta, and after linearization it's gonna be ml square theta double dot is equal to mgl theta plus u. What if I say I apply Laplace, you know, from undergraduate, right? What if? And it's gonna be assumption that there is no velocity and the initial position at 0, which is not. I'm releasing from rest, so you're gonna have ml squared s square theta of s going to the s domain minus mgl moving to other side theta of s, because second time derivative gives you s square from undergraduate control, and u of s. So theta over output over input of the system gonna be 1 over ml square s square, that's right, minus mgl, right? Huh? Gonna be ml square minus mgl, that's right? Huh? So I'm gonna plot it here, guys. Oops. I'm gonna plot it here because I want to examine all the condition I set. This is suppose this is u controller. You have this transfer function ml square s square minus mgl, right? This goes to the real output. So theta over u is this from the graduate control. This being compared with the desirable input, error signal, desirable input. I set here I want to keep it at 10 degree. You see that in the open loop feed forward path there is no integrator. Integrator, I thought is 1 over s. Do you see here? No, but there is no integrator. So your problem in the in the state feedback control law, you have to use this formula. You have to use this formula. Understand? Huh? Understand? So where you have to use this formula. But what is that here? Look at here, guys. This is, look at here, guys. We got x dot 1, x dot 2 is equal to 0, 1, g over L, right? Where we got that? Yeah, g over L. Let me see. Yeah, see, g over L, and here is 0, x1, x2, plus your u, look at here, is 1 over ml square u. 0, 1 over ml square in u. This is your original A. This is your original B. But as we know that your system, and suppose that your y is equal to, you just only want to see that the angle of the pendulum as output of the system. This is your C, the angle, only angle of that. Okay. So, but based on whatever I taught you, you have to make a hat, this, to design this controller, right, from the previous class. So what we need to have, here we go, we need to have a hat. A hat, what was? Original A 0 minus C 0. Let us put it here exactly. So your original A in this problem is 0, 1 G over L 0. Right? So it's gonna be 0, 1 G over L 0. That's right? Huh? And your C, minus C, minus 1, 0. And what you're gonna hit here? 0, 0, 0. This 0 is for this. This is your A hat. Now you have to make B hat. B hat is original B 0. So you have to make B hat, because you ordered by analytical tools I taught you in the part 16. Original B is a 0. Look at here, this is original B. 1 over ml square and 0. Here we go, we got it. Understand? Now, because your system is this, look at here guys, your system is this, after this, x dot 1 is equal to x2, x dot 2, because I added the order of the system, is 1 over ml2 u plus mgl x1, and zeta dot is r, desirable input, minus c x, c x, x is x1 and x2, side, big one. See guys, x is x1 and x2. Here we go. Understand? Now you have so you have 3. There's 3 by 3. That's right. And obviously your u, that I'm gonna put it here, u gonna be minus k by Ackermann, by using this a and b, kx plus ki in the zeta, that's now your state variable. I'm gonna put it here, but this is gonna be up there in the Matlab code. So let us go to Matlab and see what we can do. Okay, I'm gonna exactly transfer this to the Matlab. Guys, if you learn this, you can do any problem. Okay, let me see. Yeah, we have time. Before it comes up, this ki, guys, you added a state variable, that is third state variable here, guys. This is your third state variables that you added to the original system. Let me show it. Right, this is the third state variable. So your k originally was 2 gains. Third gain gonna be for this zeta. I'm gonna show in the Matlab. Okay, so third gain gonna be the third gain. You're gonna use it here. Okay, let me show you. So let me see again Matlab coding. So this is function, okay, function dx is equal to, say, pendulum problem, no integrator, t and x. Then I have to generate the space dx x is equal to zeros. Your original system is, again, please look at here. Your original system has two state variables. What we virtually added another state variable, so you have three. It's gonna be 3 and 1, right? And I said mass of the pendulum, say it is 0.1 and kilogram, for example. Length of that is 1. J is say 9.1. So the parameters. Now let me go to state variables. So dx1, as we said, is x2. dx2 is equal to 1 over m of L square, as you saw in theory, multiplied by U controller plus M G L in x1. That's right, and this is what it is. Here we go. But now we have to design U. U is control minus gain in we have now 3. Oh, sorry, I forgot this. So, and dx3, what is x3 here? Look at here, guys. This is your x3. Come on up. dx3, so zeta dot is r minus cx. dx3 is r, your set point, that can be temperature of the room, can be the speed of the car, minus c in x. Your x is x1, that's right, and x2, that's right. Right? So, but you see, obviously you have to find here, your c is 1 and 0, because you want to only measure the angle. And the r is 10 degree, but you have to make it in a radian, guys. This is very important. You have to make it in radians. Okay. So u now is minus kx, but we have this x is 3 because first you have to say gain. Okay, now let me go here. Suppose your boss says, you know what, I want to have here, got 3 state variables. Desired poles eigenvalue is going to be -1 plus j, -1 minus j, and -5. Means that I want to have a dominant. I taught you several times. Dominant pair of complex conjugate poles means that I want to have under damped system. We can change it, but this is going to vanish. That I'm going to assign for this zeta. Okay, I taught you several times. Go and see it. So, and so you have to calculate k. K is, so j is desirable poles or eigenvalues -1 plus I, or j -1 minus I, and -5, because third order system. So your k gonna be acre. Now you have to have a hat, b hat. So a, say I said h, a hat is, as we derived, is 0, 1, 0. Look at here. This is a hat. G over L 0, 0. That's right. -1, 0, 0. So it is G over L 0, 0, -1 and 0, 0. This is a hat. We changed. B is 0, 1. Look at here. B hat is 1 over ml square. That's right. 1 over ml square. I have it. Here we go. Ml square and 0. This is your B hat. We changed it. These are not original because of the things that we had say. So now let me go and make a space between them. So your J and this is, so acre gonna be A hat as I taught you, B hat, and J. Okay. Now guys, look at here. If I copy and paste all of them here, you see that we will have 3 K's gains. Here we go. Original system was second order system, guys, here, but by adding a virtual zeta as a state variable to make an integrator for the system, we have 3 now, because we increased the order of the system from 2 to 3. Understand? This is K. This is very important, guys. Okay. So, and now we have K. We can put it here, and x1, x2, and your x3, which is zeta dot. You see, zeta dot gonna be x3 plus, let me try this one, guys. K, third element is 4 zeta, that's right. K in what? Look at here, guys. I'm gonna show it to you. Oops. See, Ki in zeta. Zeta is x3. That's right. Zeta is x3. Look at here. Here we go. Zeta is x3 in x3. Let me try it, huh? Let me see. 1 in third element of that. Now I'm gonna save it. I'm gonna save it in M696. Pendulum not integrator, obviously. Now let us solve it. So it's gonna be total time and y is equal to ODE 45, as you know. Now go and call pend ni, time is between 0 and 0.1 to 10 seconds, and because you have 3 state variables and all of them start from 0, 0, and 0, 0 angle from upward position, 0 velocity, and 0 for zeta. Here we go. So I'm going to say figure 1 plot all time, plot all time and y and the first element, and multiply by now 180 because it's radian. By I'm going to see it in angle, that's right, and the blue line, and obviously grid. Here we go, and again here it's gonna be solver for peng, not integrator. First let me debug it, because obviously we're gonna have some typos and these kind of things. G over L 0 0 minus 1 0 0 would be 0 1 over L square 0, and this is this. Your acre is this. U is minus kx plus k in x3, and I'm writing here in front of this. This is added zeta as the third state variable. Please try this in home. I want that you try it in home, okay? And now this goes, oops, u plus mgn is x1. This goes for this, this goes for this. Oh, this is extra. 1 over 1 square. Everything's right now. Here we go. And here we go. That's right. And this is the control input, right? And this is gain metrics and desirable poles or eigenvalues to yield under damped inverted pendulum, pendulum. Huh? Okay. Now let me run and see what we get. What happened? Wait, this is holding. Oh my god. Hold on, guys. Okay, so guys, I was plotting here x2. I'm stupid. So now what I'm gonna run the simulation is right here, guys. What I'm gonna do, I'm gonna say, let me first plot it here. I'm gonna say, guys, this is pendulum here. Initial position at 45 degree. Now design a controller that make it at, say, 10 degree. That's right. This is what we want. That's why the initial condition is pi over 4, 45 degree. That's right. And this is, as I said, K1. I don't know why type 3. That's right. This is K1 and 1, the first element, K1. So now if I do that, look at here. Here we go. Started from 45, and this is under dam as I want, and goes to 10 degree. See? So, and if I say starting from, I don't know, 0, and keep it at 10 degree, here we go, starting at 0 upright position and comes down, look at here. Now I started from here and comes to 10 degree at the same time. This is under dam system. Huh? So you can make it critically damp. Say 1 minus 1. I don't want to have any oscillation. Here we go. Not bad. Okay. Let me make it 3. We can play with them. 2 real parts, and here it's now close to the under there. Okay. So now I want to keep it because I want to make a simulation of this. -1 minus I. Okay. So now you design the controller. Works. Now what I'm gonna do, I'm gonna say, okay, you know what? 4 K is from 1 to 1 to length of y1. I'm gonna make a simulation, guys. Okay, I'm gonna show you how your controller works. Okay. Let me see. Okay, length of that. I'm gonna say, okay, for that, figure 2, okay, plot 0 and L sine y, which is theta, K and 1. Look at here. I'm just making a movie of that by controller. Here is L sine. Here's L sine x. Here is L cosine. That's right. L cosine. Here's L sine. That's right. This is theta. I'm getting x of this point and x of this point, and y of this point and y of this point. Okay. Look at here. X of that, x of that, and again y of the base, and see that this is y of the particle mass, but this is cosine, and now, and make it blue, and the line width at 2, okay, and that's it. I'm gonna say hold off, but grid, and the axis from 0 to 2 and 0 to 2, and the end. Let me see how it looks like. But these are in the radians, right? Yeah. Okay. Let me see. What the hell is that? Oh, there's 2 here. Oh, and the L. You can say it global. Say global L. That's right. Oh, L. Yes, you define L here. That's right. What the hell is this? Global. Okay, you can say global L. Right? Global L. Because L is here. See, it's now distinguishing the L. Let me see how it looks. Oh, another park. What the hell is this? Hold on, links. I have a typo in links. TH. Okay, links. So let me see how it looks like. See? Oh, starting from 0 and stops at 10 degrees. Here we go. You just made a simulation of your controller. So let me change this as to 0.6 and here also 0.6. Let me see. Here we go. I have to increase the 0.3 here, and that's see here 0.3 and here's say 1. Here we go. Let's make it a little for 2. So you see your design controller, but the scales are not the same. I want to make it 0.1. I don't care. See? So, and it's under them. That's oscillating. That's right. So now you can say, you know what? No, I'm putting that here at pi over 4, or even more, 60 degree, and goes to the 10. See? See? Oh, starting from 16 goes to 10. But because I want to make it scalable, let me do like this. 2, I don't care, 2 and 2. See? See? But I have to put it like here. -2. That's enough. Oh. See? Here we go. Well, finally stops at 10. You see, but because of overshoot goes to that way. This is not good, okay? So that's why maybe you have to say, for God's sake, I want to make it critically damp. -5, -5, -5, -5. Here we go. Much better, that's right. But if you increase, see, much better. Goes to 10. But still you have it. So you can tune it, that's right. So I don't know, say here's -10. -10, I don't know. The poles. Much better. That's right. So, but you can remove this also at the same time. So you see that it's not doing, understand? So your controller works. So, and you have no integrator. We design the controller. Even you can plot it here. See that if you say figure 3, okay, and I want to see the controller side, plot T and U, okay, and in red and star, right, and say hold on, you're gonna obviously see the controller. That's right, you can see the controller. Here we go. This is Newton meter, because this is torque. That's right, this is Newton meter. Newton meter, I'm sorry. Here we go. Goes to the 10 eventually. This is your control input. But there is another way to do that, okay? How to do it? Okay, how to do it? First of all, let me make it 15. Second of all, I'm just saving the time, saying u counter is equal to u plus u. So I'm putting in a vector, so u for presentation, okay? But I'm putting here con is equal to con plus 1, okay? How are we gonna do that? Before this, I'm putting con 0, counter adding, that's right, and then con here as global variable, and then putting here as global variable, right? So con is con plus 1, so u goes inside this. Look at here, let me put pause command, okay? Here we go. Look at here, guys. Use this, use this, use this. But you see, but these are zeros. Why do you think? Because there is a mistake here, guys. When you say put con here and make it global, okay? So what's wrong here that it puts 0 in coding? We have to debug it. This is from scratch, a problem that you have to debug it. What's wrong? How to fix this? How to fix this problem? I give it 2 seconds to think. Yep, so this is the problem that I want to solve as a homework. That how to put this u vector respect to global definition of the counter in the UP to plot it and total, okay? But this is not critical, so I just want that you play with the code in the home, okay? So now we design everything and we are fine. We are done, guys.